All right, so this is the very last lecture. This is it. So normally for the past three tests, I've done a review on Friday. However, I have some meetings on Friday this week. So I've posted the integration review, so the review of the Unit 4 stuff that you'll be tested on. And I think I will just pre-record that and post it a little bit later. Some of the questions on the integration review, I think I chose 5 of them to be homework problems. So I won't do those problems for the um, review, or maybe I'll record them and post them later. Um, but I will pre-record the answers to the integration review besides the ones that are homework problems, and I'll have those posted soon. So right now I'm working on the full exam solutions, and I'll have those posted soon. Hopefully I'll get exam 1 and exam 2 posted today, maybe. And then exam 3, I'll have to wait until all the regrades are turned in. Yeah. So, moral of the story being that I will not be holding a review session on Friday like I normally do, but I will post answers to the recorded solutions to the integration review in a pre-recorded video on Canvas so that you have those answers besides the ones that are homework problems. Oh, tripping over my words here today. Okay. Other than that, we're just going to finish up the stuff that there is to talk about. There's some stuff I'm going to be skipping. I'm really trying to focus on the things that are most important going forward. Like I said, there's some stuff that's going to get covered again in Calculus 2 that I'm just leaving for the Calculus 2 to cover again. So I want you to have a good foundation of integration. And to have a good foundation of integration, that means I'm skipping some of the more complicated techniques that I feel are just going to take away time that you could be using to get a more solid foundation of the basics of integration. So we have 4 remaining trig functions that we don't have integrals for. Because we have sine and cosine, and we know that we have those antiderivatives. But we don't have the antiderivatives for tangent, secant, cosecant, and cotangent. Right? The ones that we have right now, we know that the integral of sine x dx is negative cosine x plus c. We know that cosine x has the integral sine x plus c. And we know secant squared, right? We know secant squared x, dx. We know his integral is tangent x plus c. We know secant tangent is secant x plus c. And we have some cosecant ones, some cotangent ones. These are the most basic ones we have, but we don't have a flat out one for tangent or secant. Like I can do it if I have secant squared, I can take that antiderivative. If I have secant tangent, I can take that antiderivative. But if I just have tangent, we don't have anything for that yet. And the trick to this is going to be tricky u sub. So this is going to be u sub that might not be immediately obvious at the get-go. So the trick here is that we can rewrite tangent as sine x over cosine x. And then one of the things we said with u sub is that oftentimes choosing the denominator to be your u is a good choice. So I'm going to go ahead and do that. I'm going to let u equal cosine x. We get du is equal to negative sine x dx. And if we solve for dx, we get 1 over negative sine x du. So our denominator is u. We are replacing dx with 1 over negative sine x du. And that does allow our sine x's to cancel. I'm going to pull the negative out front. So we have negative 1 over u du. If we integrate this, we have negative ln absolute value of u plus c. And replacing u with cosine x, we have negative ln cosine x plus c. Now, you might think that that's the integral that we use, and some people do use this antiderivative. They use negative ln cosine x. But more commonly, so this does count as an antiderivative. More commonly, you'll see ln absolute value of secant x plus c, and I'm going to show you why. So from here, remember that if there is a number in front of your ln, you can bring it up as an exponent. So technically, this is ln absolute value of cosine x to the negative 1 plus c. So that's bringing that negative up as an exponent, which is ln absolute value of 1 over cosine x plus c, which is ln absolute value of secant x plus c. So this is often the antiderivative that you'll see for tangent. Even though they are the same, you could use either, but more often you'll see ln absolute value secant x plus c. But negative ln cosine x plus c is also valid. Now, for secant x dx, there's a lot more trickery, and I'm not going to go through the trickery of it. I'm just going to give this one to you. Just trust me, is what I'll say here. Just trust me. This one here is equal to ln absolute value of secant x plus tangent x plus c. And there's a comment, only if there's a negative in front, we change it to secant x, right? Yeah, so that's just because this is a common integral. So like if you see a list of integrals, you'll see tangent on it, and it'll be written like this. The reason it's written like this is because it's nicer to not see a negative out front. But these are the same. You don't have to change them. It's just that when you see a list of integrals and you see tangent on it, it'll often be written like this and not like this. That's all. So you don't have to do it. It's just, yeah, no problem, no problem. So what I would like you to try, though, using the same idea for part that we did for part A, try finding the integral of cotangent x. Don't worry about the fancy stuff at the end. Worry about this process right here. So cotan is the reciprocal of tangent. So this is cosine x over sine x dx. Try doing that same process that we did for tangent to find the antiderivative of cotangent. Go ahead and do that. I'm going to give you guys like 4 minutes to do this. Should be some pretty quick U sub. All right, how is this guy coming along? Good, good, excellent. All right, I'm just going to do this quick U sub. So I have U is equal to sine x, doing the same type of technique. We have du is equal to cosine x dx. So dx is equal to 1 over cosine x du. So you have cosine x over u times 1 over cosine x du. In this case, the cosine x's cancel completely. So we just have 1 over u du, which is ln absolute value of u plus c equals ln absolute value of sine x plus C. And we don't need to do any trickery here. We can just leave it like that. This last one down here also has trickery that we're not going to talk about, so I'm just going to give it to you, and you're going to accept it because that's just kind of, if you want to see a proof of it, you can easily find proofs of this online, but it's a little bit of trickery, so I'm just going to put that one in there. So there are our remaining four trig integrals. Any questions on the cotangent one that you just tried? Okay. So on the next page is a recap of all of our rules. Now, there were a few additional rules that we talked about, but this one includes all of our new trig rules. So these are kind of like the basic trig rules that we had because of our derivatives. Here are the new trig rules that we just got. If I'm being honest with you, the only one I could ever think of a teacher like wanting you to have memorized would be this tangent one down here. Most teachers aren't going to care if you have, especially these bottom two, memorized. This one is typically what you see. Some teachers want this one, but very few, granted, I can't speak for all teachers, very few want you to have these bottom two memorized, just because they're less frequently used. So the other integrals that we talked about, the ones that are saying on page 196, those ones are going to be the ones where it's like sine ax plus b dx. We said that integral was -1/a cosine of ax plus b plus c. We had one for cosine as well. And that one was 1/a sine of ax plus b plus c. E raised to the ax plus b dx. This one was 1/a e to the ax plus b plus c. And then we had 1/ax plus b dx. This one was 1/a ln absolute value of ax plus b plus c. I think that was all we had. Can't even remember where those are now. Let's see. Just going to go back in time and well, who knows? They were somewhere. Oh, here. There they are. Yep, those were the four. Right? So from here, it's really just practice. And like I said, there's some techniques that I'm just not going to cover. One of them is long division. I'm just going to surpass that and just go forward. There's some techniques that I think you'll get another chance to practice in Calc 2. And long division is kind of one of those things you'll see again. I want to focus more on our core techniques. So let's do some inverse trig functions. So our typical U substitution won't work in every situation. So for instance, this guy right here, if you try to do your typical U substitution, you're going to run into some issues. It's not going to work out. But if you look at this, I see a 1 minus e to the 2t in here. And I do, in my memory, have somewhere along the lines a memory of having an integral of 1 minus x squared dx, 1 over the square root of x minus 1 over the square root of 1 minus x squared dx. This one right here, this integral was sine inverse of x plus c. So I have that memory in there. And I feel like I could use that idea with this guy. Now, this is something I can do because I've seen it before. The more integrals you do, the more you'll see the connections. This is something you may not see right away. I'm going to rewrite this as e to the t over the square root of 1 minus, and I'm going to rewrite e to the 2t as e to the t squared. E to the t squared. Because those are the same thing. Now, if I let u be e to the t, because what I really want is I want an x squared right here, not an e to the t. So if I just pretended this guy wasn't here and had a u there, that would look very similar to what I'm going for. My du is going to be e to the t dt, and solving for dt, this will be 1 over e to the t du. So I have e to the t over the square root of 1 minus, now it's, instead of an e to the t, it's a u squared, times 1 over e to the t du. And these e to the t's will then cancel. So now I have 1 over 1 minus u, the square root of 1 minus u squared du, and that is exactly my integral for sine inverse. So this will be sine inverse of u plus c, and then replacing my u, we have sine inverse of e to the t plus c. So when you're doing these u substitutions, you're kind of thinking about what you want. Like, I would like it to look like this. Okay, if I want it to look like this, what substitution would I have to make it look like this? And that takes practice. It takes practice, practice, practice. But can I answer any questions on this particular substitution? I want to give you one that's similar to this idea right over here. In a similar vein, try this guy out. The integral of 1 over 1 minus 4x squared dx. Be really careful with this one, right? Be really careful. It's in the same vein as the other one, but try the u substitution on this. Try figuring out what you need your u to be, right? And try this guy out using that same technique we just used. I'm going to go ahead and give you 4 minutes to do that. All right. So let's go ahead and try this one out. So the key on this one, same idea, but I can make the 4x squared, into the quantity of 2x squared. This is really important that you have it as the 2x in there being squared. So I have the quantity 2x squared. Then I can let my u be 2x, my du is 2dx, and my dx is 1/2 du. So I have 1 minus, now it's u squared, times 1/2 du. Just going to bring that 1/2 out front. Once again, we have that sine inverse integral, sine inverse of u plus c, and now we have 1/2 sine inverse of 2x plus c. How did that go for everybody? Pretty close? Went well? So the key is getting that 4 to be a 2x as opposed to just doing the x squared. Now, if you're looking at this integral in the wild, right, and you have no context, you might be tempted at first to try u substitution with u equal to 1 minus 4x squared. And I like to think of my ability to do integrals as my superpower. It's a superpower you develop, but it is a superpower because I can look at this integral and know exactly what will and what will not work. And I know that letting u equal 1 minus 4x squared will not work. I can look at it and tell you right away without lifting a single pen or paper that it's not going to work, because in my head, here's what I'm doing. I know the derivative here, negative 8x dx. I can tell in my head I'm going to have 1 over negative 8x du. And then I'm looking at this, knowing that this derivative is going to have x's in it, and seeing that there aren't any x's to cancel out. So I know right away, if I tried to make this inside part here equal to u, that won't work, because I know that I'm going to end up with an x in a denominator. There's no x in my numerator, so nothing is going to cancel. And that is something I've learned from doing enough of these. And you do develop this superpower. You just see it. You can look at it and you just see it. Your brain doesn't even go through conscious steps. It just does it. That's what happens when you do enough of these. And it will happen. If you do enough of these, it will happen. You can't avoid it. You can't say, oh, no, my brain isn't quote unquote smart enough for it. If you do enough of these, your brain will unwillingly develop the superpower of just seeing what will and will not work. I promise. Practice, practice, practice. But can I answer any questions on these guys? All right. Okay. So if we look down here at this one, this is another one I'm going to have you guys do, but I'm going to take a moment before we do this one. There's going to be u sub here. What do we think we should do for the u sub here? Because we kind of have options, right? Like you could go u equal to like the whole denominator, right? You could go u equal to maybe just the inside of the parentheses. You could go u equal to maybe the ln x, or not x, w squared. You could go u equal to ln, ln w. So you have like a lot of directions that you could kind of go here. One substitution I can tell you that will never work, and maybe this is worth pointing out. One substitution that is never going to work for you is u equals w, or u equals x. When you do that substitution, all that's going to happen is you're just going to replace your variable. So nothing good will ever happen when you do the substitution u equals w, or u equals x, or u equals any single variable. It's just nothing good will happen. You can try it out, but you'll just end up with an exchange of variables. So if I'm giving you these four options, I want you to pick which one speaks to you in your heart based on the things that we've done in the past. And I want you to try this one out. You do have your list of integrals on the other page. So if you're, going through it, just try something. And feel free to use the list of integrals on the other page. Give it a go. I'm going to give you a 2-minute head start, and then I'm going to start kind of slowly going through it to give you an idea of where you should go. So I think in 2 minutes, I'm going to pick one of the U's that will actually work. You pick the one that you think will work, and then in 2 minutes, you can look up and make sure that you picked the right U. But I'll kind of go through the beginning part of it silently so that you're able to think. All right? How is the start of this problem going? Tried the second U, pretty smooth. So with the second U, were you having some issues on that one? Yep. And see, the thing I want you guys to not be afraid of is choosing the wrong U. Totally normal to choose the wrong U. You try it, when things start to look kind of weird, you just toss it and try something new. Someone tried the third one, same idea. Some stuff started kind of getting weird on that one. You should end up with the same derivative. Yeah, the same derivative. So like if you did the du on this guy here, you're going to end up with 2 ln w times 1 over w. And it's not going to things aren't going to cancel because you're going to have this ln w. You end up with the same derivative over here too. Your du is 2 ln w times 1 over w. So those ones aren't going to quite work out there. In general, if you see an ln sitting around your integral, there's a really good chance that ln is the u. Most of the time when there's an ln, it's going to be exactly the u. I'm going to go ahead and finish this guy up. But these w's will cancel. We have a 5 over 1 plus u squared du. You can pull this 5 out front. And you may need reminding of which integral this is, but you do have an integral list you can look at. But 1 over 1 plus u squared, that's going to be tan inverse of u plus c. So then I can just put my ln w right back in here. Something I want to note, because I feel like this is important to note. You'll notice that I don't have an absolute value on the w here. It would actually be incorrect of me to put an absolute value on this w. So the only time you're putting an absolute value on the inside of ln is if you have integrated 1 over u or x, 1 over x dx. This is equal to ln absolute value x plus c. The only time you're doing this absolute value is if you've gone from a 1 over x situation and you've integrated. In this situation, I wasn't integrating 1 over x. I was simply plugging my u back in. So there's no need, and it would be incorrect for me to put absolute values on this w because I wasn't integrating a 1 over x or a 1 over w. Does that make sense on that situation where you would put them in versus where you wouldn't? Excellent, excellent. Pause for just a sec. All right. So we're gonna do a little bit more here. Try some stuff out here. So looking at this integral, right? As brand new calc students, right? Well, not really brand new. We've had a semester of calc, right? But brand new integration calc student, looking at this, I would say a good thing to look at first of all when I look at this is say, hey, let's let, I know that like this guy is going to have an x with his derivative and we have an x up here. Maybe what we can do is let the denominator be u. That tends to be a good choice. So let's try it. Let's try. And I mean, you can probably tell by the tone of my voice that it's not going to work, but let's try letting denom equal x squared plus 1. Not denom equal u. Oh, goodness. Equal u. So, letting the denominator equal u. We have u equals x squared plus 1. I should do that in purple. Undo. Just because we've done purple for u. Our du would be equal to 2x dx. Our dx is equal to 1 over 2x du. Now something strange is going to kind of happen here. So I have 9x plus 7 over, and now the denominator is u, and then I have 1 over 2x du. And you have to be really careful with your algebra here. You cannot cancel these x's out. You cannot cancel those x's out. 7 doesn't have an x on him. So the only way you could cancel the x's is if everything had an x in it, but not everything does. So nothing will cancel here. There's no way to cancel out that x, and we can't integrate when we have an x involved if we figure out a du. So this ends up being a dead end. The trick here, and this is a trick that you haven't seen yet, so it's new. The trick is we can split this up into 2 different fractions because we can, with the numerator, we can split up. So it's this guy over this plus this guy over this. So with fractions, if you have a plus b over c, this is equal to a over c plus b over c. You can break up the numerator. You can't do it with the denominator. You can't, it doesn't work the other way around. If you have like a over b plus c, you can't do this as a over b plus a over c. It doesn't work that way. But it does work with the numerator. You can split the numerator up into two different fractions, and that is the trick here. The key is seeing a trick once so that it's in your toolbox. I don't expect you to come up with these tricks the very first time. It's seeing it once and having it available to you. So I'm going to split this into 9x over x squared plus 1 plus 7 over x squared plus 1, which from there I can split it into two separate integrals, and I will tell you why. I know that this integral will work with u substitution, right? U substitution will work here because I'll have this 1 over 2x du part, and the x's will cancel. And over here, this guy is going to be a tan inverse, right? You can take the 7 out front. You have 1 over x squared plus 1 dx. That's going to be 7 tan inverse x plus c. That's just tan inverse. So we can do this same substitution that we did before with the 9x over x squared plus 1, that first part of it. So we have 9x over u is x squared plus 1, so u, times the dx turns into 1 over 2x du. The x's cancel, right? I'll just rewrite this as 9x over 2ux du. You can see the x's cancel, and you can bring the 9/2 out front. So you get 9/2 ln absolute value of u plus c, 9/2 ln absolute value of x squared plus 1 plus c. Now, what I will tell you is that very, very technically in this case, you don't need the absolute values, and I'll tell you why. And I wouldn't expect you to necessarily catch this. I would rather you just leave the absolute values in, but x squared plus 1 will always be positive, so those absolute values are doing nothing because there's no way x squared plus 1 could be negative in the first place. So telling me that a positive number will be positive is just a useless statement. So in this very particular case, we don't have to worry about the absolute value, but I'm going to leave it there. So we had the integral of 9x plus 7 over x squared plus 1 dx. Now we have our two parts of it. So the first part is the 9/2 ln absolute value of x squared plus 1, plus the second part of it, 7 tan inverse x, and then we'll just put one generic plus c at the end. And there we go. Questions on that integral? Okay. All right. So let's look at this next guy. So we have the integral of v over v to the fourth plus 1 plus cosine 5v minus 4 dv. This is another situation where these integrals need to be split up because one of them is going to need u sub and the other one either uses u sub or you can use one of our special rules. But this has to be split up into this guy, dv, plus this guy, dv. Now, if you remember, we had a special rule for this cosine case. So this one could be done really quickly. This guy over here is going to require u sub. And you're going to have to figure out what that u sub is. Now, I'm going to tell you that tan inverse is going to be involved somehow in this guy. The antiderivative is going to involve tan inverse. So think of the setup of tan inverse and what you would need to make u equal to in order to make tan inverse happen there. Right? This guy will be fast, but let's look at this guy. I'm going to give you a minute to think about it. And then I'm going to tell you the direction that you should go and then give you a chance to finish it off. But I'm going to give you a minute to think about how you should arrange this if you want that antiderivative to be tan inverse. Okay. What thoughts do we have on this guy right here? What thoughts do we have on what u could be? No wrong answers. There's things that won't work, but there's no wrong answers because we're all just trying stuff here. So I hear a v to the fourth. Any other ideas on what we could do? I hear a v squared. A v squared. V squared is very clever. So with this guy, if we rewrote this, and I told you tan inverse was going to be involved, right? I told you tan inverse would be involved, and for tan inverse, we have a 1 plus x squared situation. I told you tan inverse is going to be involved, so we want it to look like 1 plus x squared. So if I rewrote this as v squared squared plus 1 with a v on top, now this kind of looks like this setup. And indeed, using v squared here will get you to the right answer. Now, if you use v to the fourth, you could totally try it out, right? Totally try it out. And then you'd find, so here's what my brain is doing. I know that the derivative of v to the fourth is going to be 4v cubed, and I know I don't have a v cubed in the numerator to cancel out, so immediately that's why I start to feel a little hesitant to do that. But it's cleverness, right? This is all just about being clever and lucky, trying a bunch of things out. And don't be afraid to try the wrong thing. It's okay to try the wrong thing. Especially this is a take-home exam. For the final, all of them have been take-home, and your homework is take-home, obviously. You can totally make mistakes on a separate piece of paper, and then once you get it right, copy it over. And you don't have to worry about the time constraints that you'd have in a classroom. So you have tons of time to be wrong. And you should embrace being wrong and then just starting over. It is how you become a good mathematician. All right, so if I redo this guy, then I have u squared plus 1 times 1 over 2v du. These v's will cancel. I'm going to bring the 1/2 out front because there's that 1/2 right here. And I have 1 over u squared plus 1 du. Same thing as 1 plus u squared. So this is 1/2 tan inverse of u plus c. So 1/2 tan inverse of v squared plus c. For this other guy, remember that you have the integral of cosine ax plus b dx is equal to 1 over a sine ax plus b plus c. This is the exact same situation. So cosine of 5v minus 4 dv, that's going to turn into 1 over 5 sine 5v minus 4 plus c. So our total integral love the convenience of technology. Point. Is going to come out to be 1/2 tan inverse of v squared plus 1/5 sine 5v minus 4 plus c. How did that go? Good. How does everyone feel about that? Pretty good. So it's practicing. Practicing. All right, I'm going to go ahead and go to the next page. So the last thing for us to cover, because we've covered u substitution, but we've only done it with indefinite integrals. We've done definite integrals, but we haven't done u substitution with definite integrals. And that is what we have left to talk about. I'm going to tell you there are 2 different ways to talk about u substitution and definite integrals. I find that if I talk about both ways, that what ends up happening is students make a hybrid of the 2 in their head and get answers completely wrong. So I'm going to teach you only one way. I'm going to tell you that there is another way out there, but that I'm not bringing it up, so that if you go online and you find this other method, that you understand that it's not me holding back on you, it's me trying to only give you one so that you don't make a hybrid of the 2 methods that gives you a wrong answer every time. So I'm going to teach you one method and one method only. There are other methods out there. There's my disclaimer. All right, so this is going to be a u substitution problem. And the u substitution problem is going to start out very similar to how we've done u substitution in the past. In particular, you start by choosing a u. So oftentimes, the inside of something with an exponent is a good choice for u. So I'm going to do that. I'm going to do x squared plus 1. My du is equal to 2x dx. My dx is 1 over 2x du. I'm going to leave my bounds alone for a moment, so I'm going to give myself a little bit of space here. So this will be 2x u to the 4th times 1 over 2x du. What's left is dealing with these here bounds. These bounds are what is left for us to deal with. These values up here that we are given are x values. This is from x equals 0 to x equals 1. Those are x values because our original integral dealt with x's. We need to change those x values into u values so that when we integrate, We have u values everywhere. All right, so I'm just going to keep them in the same order they're in, right? 1 on top, 0 on bottom. If x is equal to 1, maybe I'll give it a little space. If x is equal to 1, we can use this formula for what it should be equal to in terms of u, right? U is equal to x squared plus 1, so u is equal to x squared, 1 squared, plus 1. So that would be 2. I guess I don't need that space, little space. So this guy right here, where we did have a 1, we are now putting a 2. Here we have 0 squared plus 1, which would just be 1. So where I had a 0, I am now going to put a 1. I am replacing my bounds with their new u values that I'm getting from this u right here that I have already determined. Because you've done this, you don't have to do anything. You don't have to substitute u back in ever. So I know that these x's right here are going to cancel. And I'm going to have 1, 2. Also, these 2's cancel. The 2's and the x's both cancel. U to the 4th du. That's 1 over 5 u to the 5th from 1 to 2. You don't need to plug u back in. You can just plug in as if this were any other definite integral. So don't plug x squared plus 1 back in. We're just going to go and evaluate this the way that we've done all of our definite integrals. So we have, I'm just going to leave the 1/5 on the outside. This will be 2 to the 5th minus 1 to the 5th. Right? 2 to the 5th is 32. 32 minus 1, 31 over 5. And there's your answer. And this is because you'd have 1/5. This would be 32 minus 1, which would give you 1/5 times 33, or sorry, times 31, which is 31 over 5. And it's just like that. The only thing you have to do is you have to remember to change your bounds so that they are u values. I find that it's easiest to list your bounds in the order they come. So even though like this is the lower bound, this is the upper bound, I would always choose to write them. This is 1 on top, 0 on bottom, 1 on top, 0 on bottom. Because if I wrote 0 first and then 1, my brain's not going to be very happy about that. My brain is going to try to flip them. So I just try to keep them in the same order. Not so bad, right? That's not so bad. It's just like one extra step. Yeah, exactly. Just one extra step in there. There's a lot of room on this example because typically I would go over both methods. But like I said, I'm not going to go over both methods because it just gets people confused. So I want you to try out this example. I'm going to give 2 minutes and then I'm going to slowly start filling in the steps, right? So choose your u. There should be a fairly obvious choice of u in this one. Change your bounds, do the substitution, do the plugging in of numbers. After 2 minutes, I'm going to start slowly writing in the answers without saying anything, so you can kind of check your work. I have wrote the beginning parts of this problem up. I'm going to give another 2 or 2.5 minutes for you to finish it out, but I do have the beginning parts written up if you want to check where you are. All right, how is this one coming along? Okay. Something I want to point out that might make you kind of uncomfortable. So you might notice when I changed my bounds, like it's supposed to be lower bound, upper bound, but you'll notice here that the bounds look like they're all messed up. Like it's like 8 to 2 instead of 2 to 8. And you might feel like, oh, I should flip those around then to make them right. Don't worry about it. It's okay if this gets out of order. Just make sure that, like, I plugged in 2, right? And I got 2. I plugged in -1 and I got 8. Just make sure that bottom, bottom, top, top. From here, I can pull out a 2 in this first group. And let me actually... And on the bottom, I have 6w minus 5 du. So I can cancel these 6w minus 5s. And I can pull that 2, this 2 right here out front. And I have e to the u du. So I have 2 e to the u evaluated from 8 to 2. So I have e squared minus e to the 8th. And there's no more I can do there. I just stop right there. Can I answer questions on that one at all? So it's because it's about getting tricky, especially with the canceling step. So oftentimes there's some factoring that needs to be done to make things cancel the way that they should. Can I answer any questions on that one? All right. So let's just do another one. This is another, just try stuff out. I want you to try this one. This is another, it's going to be a U substitution problem. I'm going to give you 5 minutes. I'm going to let you do the entirety of it. I'm going to give you 5 minutes to just do the whole thing, and then we'll go through the answer of it. But I want you to give it a try because honestly, I know it just feels like a bunch of me saying, you try, you try, you try. But that's really the best thing you can do for yourself is just try these problems out. It's not going to do you much good to just simply watch me do the problems. It's going to do you good to practice them. So that's why I keep on giving them to you for trying. I'm sure it makes the recordings very, very short because a lot of it is silent time where I've stopped recording, but it is important that you try these out. So go ahead and try this one. I'll put a 5-minute timer on and then we'll come and we'll talk about it. All right. How is... Oop. I'll get myself tangled in my cord. How's this one coming? How are we doing on this one? Great. I love hearing a great. That's my favorite one to hear. Not sure if my answer's right, but you did get to an answer. So that's looking good then. So let's see. So here, a good choice for you is going to be the denominator. For your du, you're going to have cosine t dt. Solving for dt, you have 1 over cosine t du. For your upper bound, so your t is equal to pi over 2. Your u is equal to 2 plus sine of pi over 2. Sine of pi over 2 is going to be 1, so this will come out to be 3. For your lower bound of 0, we have 2 plus sine of 0. Sine of 0 is 0, so this comes out to be 2. We have a cosine t up in the numerator times u, or over u, times 1 over cosine t du. These cosine t's will cancel. So we have the integral from 2 to 3 of 1 over u du. That integrates to ln absolute value of u from 2 to 3. So that's going to be ln, the absolute value of 3 is just 3, so ln 3 minus ln 2. Now, if you wanted to be really fancy and use your ln rules, you could say this is ln of 3 halves because it's the same thing. Either of those we're going to be fine answers. Sometimes you just want to, you're just feeling extra fancy. Got it right. Excellent. Excellent. Yeah. So sometimes these answers, I know, like Sometimes it's like, oh, I don't know, this answer is not coming out to be a nice number. Sometimes they just don't come out to nice numbers, and that's okay. Any questions or comments on this example? Right, when you take the derivative of sine t, it's positive cosine t. But when you take the antiderivative of sine t, it's negative cosine. So it gets confusing. But the derivative of sine x is positive cosine x. The derivative of cosine x is negative sine x. But on the other hand, the integral of sine x is negative cosine x plus c, and the integral of cosine x dx is positive sine x plus c. So this is, I mean, I've had this conversation a few times about how it's a little bit confusing the way that semester systems have to do calculus because we have to talk about this all at the same time. But this is, I think, one of the most confusing things is the brain trying to handle the sine cosine connection because it's positive in one direction and negative in another. And I wish I could tell you a cute brain trick for memorizing it. But I can't quite verbalize what my brain does to make the connection between the two. I guess, like, for me, I think of derivatives first and then integrals, and I think of sine as being better than cosine. So I think of sine goes to positive cosine when you think of the first direction, which is derivatives, and then I don't know. That's the best I can do to verbalize what my brain does to think about it, because I need something cute like that in my head to memorize things because I'm not good at memorization. You'll have to find something that works, though. Maybe there's something out there that would help, but it is a confusing connection. Any other questions on this one? Okay. Let's see what remaining examples. So I know I'm not going to talk about this example. I'm tempted to kind of leave off this one too. I think I might take this time right now. We have 20 minutes left. I don't think I'm going to take the entirety of my 20 minutes left. But I just kind of want to talk about what we have going on at the end of the semester, because I kind of talked about it in the very beginning, but I want to just make very clear what's going on. So things that are left that are due, like remaining due things. Remaining stuff that's due. So due tomorrow, which is, I guess, 12-3, and it's a Thursday, is the exam 3 regrade. Due on Monday of next week, which I believe is December 7th. Let me just check my calculator. Or not calculator, calendar. Monday, 12-7. That will be homework number, I think it's 10, which is posted. It is 10, isn't it? Yeah. And then the final exam is going to be posted on Monday. 12-7, and it will be due on Friday, which is 12 dash, I don't know, 11. So if I kind of draw a small little calendar out, and today is the 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th. And here we are. This is today, right here. All right. So looking at this calendar, things that are due, the regrade, the exam 3 regrade, E3 regrade, that's due. If I can write tomorrow. All right. Monday, homework 10 is due. The final exam will be posted. I'm going to write FE, posted. And the final exam is due on this Friday. I cannot extend this due date any longer because as an instructor, my grades have to be in by this day right here. Grades due for instructors. So this right here is already kind of pushing it. So it gives me the weekend to grade. It gives me Monday and Tuesday to grade, but I can't push that due date back to Sunday because that doesn't give me enough time to grade these exams and make sure everybody's like homeworks that they've turned in are due, are done. So I also am teaching another class where the due dates are out of my control, and the due date for that class for their final exam is this Sunday right here, which is 2 days before grades are due. And I have 150 students in that course. So these 2 days are already going to be preoccupied with a lot of grading for that course. So I'm just trying to explain to you that why I absolutely cannot postpone this Friday deadline. So you will have these entire 5 days to do the final exam, but that deadline won't be moved at all. So it's really important that you work on it during the week and don't anticipate me moving it because I can't move it because I physically do not have enough time in the day to grade everything that needs to be graded. The other thing to mention is that if you're going to make up any old homeworks, those are going to be due this day too. So any old homeworks that you haven't done, something you have a 0 on because you didn't turn it in, those are due on the 7th. It might say the 6th, but the 7th. Turn in any missing homework by December 7th. Right. Any missing homework that's turned in after December 7th, I am not going to be able to grade. There's just a lot of stuff that has to be graded. So, looking at the calendar, that's what we're looking at. I posted the integration review, and the integration homework 10 includes 5 problems from the integration review. The integration review is all the Unit 4 stuff you need to worry about. Anything that's not on the integration review, minus, I guess, some of the area stuff that we covered in homework 9, is like, but you really just need to worry about the integration. I'm just mostly concerned about the integration. I will be going and doing a video on my own time, hopefully before Friday, maybe, that goes over all the problems on the integration review, except for the problems that are included on homework 10, because I want you to do those problems. And I will post that video sometime in this range here. for studying for the final exam, I would go over your old homeworks. I would go over your old exams. I hope to have all the exam solutions posted by this Friday. So the exam solutions for exams 1, 2, and 3, I hope to have posted by this Friday. But go through your old exams, go through your old homeworks, go through your all the old reviews. I have 3 old reviews plus the review videos for those, and I'll have the integration review up. So go through all that material, go through the homeworks, go through your exams, and go through the reviews. And that is the best you can do to prepare yourself for the final exam. You also have an entire week to do the final exam. Well, an entire 5 days to do the final exam, which is a lot of time. Yeah. I think that's, I'm just thinking about things that need to get covered. I think that's about it. Does that make sense to everybody about like what the rest of this semester looks like? I just want to be very clear so that it's clear for everybody. Good. Excellent. Okay. So with that being said, this is it for the lecturing portion. This is all there is for it. You have finished all the material you need to know for Calculus 1. There won't be any regrades on the final exam for the reason that there's not time. There's not time for me to grade it and then give it back to you and then have you redo your final exam. There's just not time for that. So, unfortunately, you won't be able to do any regrades on the final exam, but your lowest exam score will be dropped and replaced with your final exam if you do better on the final. So if your lowest exam score was like a 20%, you could have it replaced with maybe you did 80% on the final, you could have it replace it. The final exam is not optional. Let me be very clear, because sometimes students get confused with my dropping policy and they think, oh, if I did well on exams 1, 2, and 3, then I don't need to take the final. And that is not true. The final exam is worth, 30% of your grade. It's worth a large portion of your grade. Let me just double check what it is, because every class I have, it's different. So, where are you, syllabus? There you go. 20% of your grade. So your final exam is worth 20% of your grade, which means that if you choose not to take the final exam, your grade is going to go down by 20%, like 20 whole percentage points. So the final exam is not optional. It doesn't get dropped. The final exam does not get dropped. The only thing the final exam can do is it can replace a lower exam score. So it can help you by being better than a previous low exam score, but you can't rely on your exam 1, 2, and 3 grades to carry you through the end of this class. You have to still take the final exam. I mention this because I have had students who opted to not take a final in situations where they absolutely had to take the final. So I like to mention it. Okay. I've blabbered on for long enough at this point. That is the end. I really appreciate all that you guys have done. Oh, there's a question. If your lowest exam is higher than your final exam grade, does your final get replaced with that? No, I won't do that to, so like if, I think I know what you're trying to say here. Like, let's say you got like 90, let's say you got like 90s on all of these, and then on the final exam, you got like a 70. I would not replace anything. So like you would still have this would still be worth 20% of your grade. But these scores would stand. I wouldn't replace it. The only time that this would get replaced is if you instead did like 100, and then like one of these would turn into 100 as well. Does that make sense? Yeah, no problem. So if you have any questions on anything, you're always welcome to email me. Obviously, you're going to still hear from me because we're not done with the semester yet, but we're getting there. So there are no lectures next week. I need to make that very clear. There's no lectures. We're done with lectures because this is the last week of the semester. Next week is all final exam. You can email me. You can ask me questions. It never hurts if you're really stuck to ask me a question. It never hurts to do that. The worst I can say is, I'm sorry, I can't give you that information. But the best thing to come of that is me clarifying something that you need clarified, or getting a hint that you need to move forward. So please don't hesitate to reach out when you need help. I am more than happy to provide that help. I just want everybody to get what they want out of this class, which I believe what everybody wants is just to pass the class and move on. But I am here to answer your questions. I am not going to disappear. I hope that you guys have a fantastic rest of the semester, because we won't be doing a lecture anymore. And yeah, I'm going to stop blabbering. It's been really great with you guys. I'll stop the recording now.